All right, here we are. Let's see if everybody's shown up just about. All right. All right, so what are we doing today? Well, we have several important things to do. First of all, we have a little bit more to go in chapter 8. There's some topics that we were not completely finished with. So we'll start there. We also have some videos, which is always fun. So what I'd like to do is point out that since we're basically done with chapter 8, there is on Moodle, let me go find Moodle here. I guess I lost it. All right, let me go get it. So yeah, over here you'll see that there is a chapter 8 problem set. And so after today, we'll be ready to do this one. All right, so you can see it's fairly long and it covers everything we've done up to this point in chapter 8. So what I'd like to do is have everyone work on this for next Monday when we will go over it. And then when we're done with chapter 8 today, we'll actually start looking at the next chapter, which is actually chapter 11. All right, it's not 9, it's not 10. We're doing 11. And so 11 and 12 actually sort of go together with each other. They represent our introduction to what we will call probability theory and statistics. Now, they're very, very different than what we've done up to this point. They're a little bit more theoretical, and but they're also extremely useful for many different applications. So I think you'll find it actually to be quite interesting, and it certainly is useful. So right now, why don't we go back to our discussion in chapter 8, where last time we did a lot of annuities, but now what we want to do is look at two different methods for quoting interest rates, which we haven't really discussed up to this point. It turns out that if you go to a bank, for example, or you want to borrow money, or if you want to put your money in the bank, or any other situation where interest rates are involved, there's two standard ways of expressing interest rates. So the first one, as you can see here, it's called APR, which stands for annual percentage rate. And here's an important note. Sometimes this is known as the nominal rate. They both mean the same thing. And what this is all about is that this rate tells us how much simple interest we're being paid or we are paying if we are borrowing. All right, so APR is simple interest only. Now, as it turns out, in the formulas that we've been using, like this present, let me copy this back here for a second. This formula that we've been using, among others, let's see where I can sneak this in here. Oh, that's good. All right. So I just wanted to point out that in this formula for the future value, this little r here actually is the APR. That is what we mean by the annual percentage rate, and it reflects simple interest only. So what other kind of interest rate could there possibly be then? Well, it turns out the next one is referred to as the effective annual rate, sometimes EAR, or sometimes it's simply called the effective rate. And this rate, unlike APR, reflects both simple and compound interest. That's an important detail, okay? Because realistically, that's the one that you need to know because it determines how much you're earning on a bank account and how much you're paying on a loan. Okay, so that's why this number matters so much. What we are going to do in this chapter is figure out how to calculate the EAR once we are told the value of the APR and the compounding frequency, because it'll turn out that the difference between the two comes down to compounding frequency. That's what really separates the two rates. Now, if you go to a bank, let me just go to the internet for a second and see if I can come up with an example of this. Typical bank savings rates, APR, and EAR. Let's see if I can come up with a quote from a bank, an actual bank. Oh, I guess maybe not. Mm. All right. We won't do this then. All right. So here's what we're going to do. Let's imagine that you walk into a bank and you say, I have money that I want to invest in a 5-year CD. Remember, CD is a certificate of deposit. With a 5-year CD, you are required to leave your money in that account for 5 years. But of course, in exchange for that, you get more interest than you would get with a traditional savings account. So you walk in the door and you see a sign and it says, oh, over here, here's where we show you the quotes we're currently offering for 5-year CDs. And you look at the sign and you notice something interesting. There's 2 numbers. Now, they usually, if they do label these, the labels, in other words, the letters underneath will be really tiny, so you can barely see them. But there will be 2 numbers next to each other. And so in our example here, we have 1.02% and 1.04%. So you probably wonder, why are there 2 numbers? And it's because the one on the left, the smaller number, is the APR, which means your simple interest is 1.02%. On the right is the EAR, or effective annual rate. That's what you're actually earning when you take into account your compound interest as well as your simple interest. So the one on the right is how much you're actually earning. That's why it's such an important number. So here, the difference between the 2 is pretty small, but the one on the right is obviously larger than the one on the left, which means that you're actually getting more interest than you may think you are if they only told you the APR. So most banks do quote both numbers. The ones who don't typically show just the one on the right, the EAR. So now most people who go to that bank do not know why there's 2 numbers, but now you do. Okay, you're part of an elite group of people who actually understands what these interest rates refer to. So what we're going to do next is show how you can take any APR and combine it with a compounding frequency and convert it into an EAR. And when you see the formula, you'll say that it looks awfully familiar. It's very similar to what we've been doing up to this point. Specifically, if you look at it very carefully, this formula does closely resemble the formula that we've been using to calculate the future value of a sum. So there's a lot of similarities here. And I just want to point out that this R, as I've already mentioned, R is, of course, the APR. And you recall is the compounding frequency. Okay, and of course, E then will represent the effective annual rate. And you can see that the formula is a little bit simpler than what we did down here, but not much. It's a very similar type of formula. And of course, what you'll see when we get to our examples is that you probably will want to simplify it before you attempt to do this on your calculator. All right, so I think we're ready for our first example. So what we're going to do is assume that we are going to visit a bank that has an APR of 3%. And what we're going to do is calculate what the EAR would be based on different assumptions about the compounding frequency. All right, so here we go. Let's say that our bank offers a 3% APR. What would then be the effective rate based on the following 3 assumptions? Compounding takes place in part A annually, in part B it's semi-annually, and in part C it is quarterly. And of course, these are the corresponding values of N in those different cases. Okay, annually means once a year, semi-annually means twice a year, and of course, quarterly means 4 times a year. So we're going to apply this formula in all three cases. And after a while, we're going to get pretty good at this. All right, so let's look at the first case, annual compounding. So here's the formula in the bottom there. Now, if you look at it carefully, you'll see that R, this is our APR, is 3%. The compounding frequency is once per year. If you plug in those numbers, you'll notice something interesting. Algebraically, after all that work, you'll see that you just end up right back where you started with the APR. And so it is no coincidence when the compounding frequency is once a year, the EAR and the APR will always equal each other. Okay, so this is a very special case. When n is 1, these two have to equal each other. After n goes up to another level, any other number, 2, 4, 12, it doesn't matter. As long as n, I'll just add this over here, and you'll see in a few minutes that this is true. When n is greater than 1, EAR will always be greater than APR. So this is a very unusual case, okay? Only when compounding is annual are they equal to each other. Okay, actually, I need to save this for a second, just in case we lose it. Which could very well happen. Okay, now for the interesting one, in part B, we're going to switch the compounding frequency to twice a year, and let's see what effect that has on our results. Okay, so n equals 2. So when you plug in these numbers at the bottom here, you'll see that you actually have 3% cut in half, but then when you add, after adding 1, you're raising that to the second power. So you can see that you can reduce this to a simpler version right here, 1.015 squared minus 1. Now, when you implement this on your calculator, if you have the iPhone, what you want to do is what you see down here, take your 1.015, hit the square button. That will give you the result that you need. Then you must subtract 1 and hit the equal sign, and that will give you this number over here, 0.030225. That's our EAR. That's what we're looking for. So you can see now, because n is greater than 1, EAR is greater than APR. And in addition, we can make the following claim. This extra piece here is our compound interest. Whereas the original 3% is our simple interest. So as an investor, you're getting 3% in simple interest and another 0.0225% in compound interest. It doesn't sound like a lot, but if you leave the money there long enough, the difference between the two will start to really matter. Okay, so in other words, the impact of compound interest makes itself felt over longer time periods. For example, more than a year, like 10, 20, 30 years, it will make an enormous difference. All right, so now I think we're ready for our last example, which is quarterly. And what's happening now is that n is now 4. So in this formula, you're taking your 3%, dividing it by 4, and raising this to the 4th power. And so ideally, you should simplify it to 1.0075 to the 4th power minus 1. Now, on your calculator, which I've moved up here, this time there is no 4th power key. What you do is use the exponential key, And that means you do need this equal sign here. So you'll go 1.0075 raised to the fourth power equals, and whatever that is, you need to subtract the 1 to come up with your final result, which you can see is 3.0339%. All right. Now, even though it wasn't originally in the slides, I've added this after the fact. We're going to do daily now. Daily means 365 compounding periods per year. And so let's take a look at that case. And so here, now the problem here is that when you simplify 3% divided by 365, it's a very, very small number. So I recommend that you do not round it too much when you do your calculations, because you're likely to run into some pretty significant inaccuracies. So 3% over 365 plus 1 is approximately equal to 1.000082192. That has to be written, we have to raise it to the 365th power before we subtract 1. And so here I've done it for you right here in this box. You can see the calculator strokes that you need. This long number is raised to the 365th power. You must then hit the equal sign, then you subtract the 1, and you should get the same thing, approximately 3.045%. The key word there being approximately. Of course, there's a lot more digits after that decimal point. We can round it down to this. That's plenty sufficient, because ultimately the interest that we are paid will be rounded to dollars and cents anyway. So we don't need to go nuts and have 18 digits of accuracy here. This is fine. In fact, in the banks, you'll rarely see them go out more than 2 places anyway. Most likely this would be quoted on the wall of the bank as 3.05%. But they would, of course, calculate the actual value for you. Now, what I've done here is I've put together a little chart to summarize what we've just done, because I want you to see the pattern that emerges from all this. And so here's the table. And so I've got the 4 compounding frequencies on the left. The APR, if you notice, never changes because it's based on simple interest. And if you remember the formula for simple interest, I equals PRT does not contain the letter N. It is not part of the calculations for simple interest. But on the other hand, the EAR clearly does depend on N. And what I'd like you to notice here is that every time we increase N, EAR goes up. When N equals 1, they're equal to each other. But after that, as I keep increasing N, EAR keeps going up. All right. Now, of course, we could have others too, but if you kept filling in this chart with more different N's, you would still see the same pattern. And in reality, in the real world, for the most part, interest is almost always compounded daily. This is the row that really matters the most. This is what you're likely to run into if you have a bank account, for example, or if you have a credit card. But it's possible for other situations to have different compounding frequencies. But for most of us as individuals, this is the one we're most likely to encounter. All right. Now, and so I've drawn some conclusions for you here as well. Again, as N increases, APR never changes, but EAR always increases. And in addition, we should note that when N equals 1, the 2 are equal to each other. All right, now, just to reinforce all this, we're going to get some practicing done right now, as a matter of fact. I've created a set of practice problems so you can get some practice right now and make sure you really understand what we're doing. Are you ready? Are you ready? Do you have that phone right in front of you or that calculator, as the case may be? All right, I'll give you a minute to catch up and then we'll get started. So what I want you to notice in this question, let's assume that the APR is 6%. Oh, hold on. Okay, good. What I'd like you to do is calculate the EAR under 4 different assumptions about the compounding frequency. And of course, I've repeated the formula right here in case you forgot. So why don't you do the first one, take a couple of minutes, do the first one, and we'll check our results, and then we'll do the rest one at a time. Okay, I want to make sure that by the time we're done here, everyone is getting the right answers. All right, we don't want to go on any further unless you're really understanding what this is all about. All right, so let's take a minute and do the first one, and let's see what we come up with. Okay, does anyone have a number? This first one is actually a bit of a trick question. I'll show you why. Because with annual compounding, even when you plug in all the numbers, oh, you'll see it's the same. Remember, this is the case where EAR equals APR. So you didn't really even have to do any calculations because you would have known if you were, I mean, it's fine that you did it, but you would have been able to say, well, listen, if n equals 1, I know right away that EAR equals APR. Therefore, my answer is 6%. Okay, so now go ahead and try semi-annual, which means n equals 2, and see what you get. And you can round it. If you get a lot of decimals, just you can round it. Not for this next one, but the next 2 will have a lot of rounding. All right, so take a minute and try the case where n equals 2. All right, does anyone have a number? 6.09, perfect. That is exactly correct. Let's see why. Okay, so you plug in the numbers, and so this simplifies to 1.03 squared minus 1. So make sure you can do this on your calculator, going from left to right. In this case, there's a square key you can use, and you should end up, in this case, it's exactly 6.09%. So it's 0.0609, which you can write as a decimal, 0.0609 or 6.09%. Perfect. So far we're flying along through here. That's great. So that being the case, why don't you try quarterly And this time you can round it a little bit. It's going to be a very messy number. You can round it to a few decimal places. But remember, with quarterly, n equals 4. So why don't you give that one a shot? All right, anyone have that number? It's approximately, yes, that looks good. 6.1, I rounded it to 6.136. Perfect. It's approximately 6.136%. I rounded it to 3 places. You can leave the rest of them if you want to. I just rounded it to 3. And so that is absolutely correct. Okay. So yeah, don't chop off that many decimals. Instead of 6, make it 6 point, let's say 136 or 6.1363. That's fine. But how did we get that? Because what you've actually got in your formula is 1.015 to the 4th power. Okay. Whatever that is, you subtract 1, and this is your final result. All right. So the last and final challenge for now is to do the same thing with monthly compounding, which of course means n equals 12. So why don't you take a minute and see what that one is? It's also a very messy result. You can feel free to round it a little bit. All right. So why don't you give that a shot? Try part 4, n equals 12. All right. Anyone have it? Let's see. That looks good. It's approximately 6.17, or I have three places. Yeah, that's all fine. Perfect. Absolutely. So any of those will suffice. So here, remember, when you divide by 12, what you've actually got here is 1.005 raised to the 12th power minus 1, and that should give you roughly 6.17 or 1.168%, something along those lines. Those are all fine. So once again, I put together a little chart for you so you can see the differences. And what's interesting is that the spread between the EARs and the APRs, well, these are of course the same with one compounding period. The gap between these gets bigger as the APR gets bigger. Okay, in other words, the larger the APR, the larger by comparison will be the EAR. If you remember, for example, let's go back here for a second, the differences were quite small. Like with quarterly compounding, the difference is 0.0339, whereas here it's quite a bit higher, 136. So the difference between the two matters more and more as APR gets larger. So why am I mentioning this? Because with credit cards, where the APR can be quite high, the difference between the APR and the EAR can be extremely significant. And in fact, in the video that we're about to watch, they make exactly that point. What they're going to tell us in the video is that while the banks will typically show us both of these rates, when you hear ads on TV, let's say for auto loans or something along those lines, what they may do is give you the APR, and you have to understand that the EAR is likely to be higher than that. So you just have to be careful when you decide whether to borrow or lend money to make sure you know both the APR and the EAR, because otherwise you could end up making some serious mistakes with your money. All right, so I think we've got the hang of this. So I'm about to show you a video which I think does an excellent job of summarizing everything we've seen here. So as usual, let me go find it and I will send it to you in the chat room. And let's take a look.
Welcome to Tillymore TV, the place to be to learn about
right, is everyone done? Okay. So anyway, yeah, so we'll wait a minute for everyone to catch up. But what we're about to do now is start chapter 11. And chapter 11, as I started to say before, is our introduction to probability theory, which will be followed up in chapter 12 by our introduction to statistics. Yes, now you might say, well, wow, that what a very different set of topics. But it turns out that these are very, very important in a lot of applied fields. And so you'll run into these over and over again in just about any discipline you might be studying. And especially in the real world, you'll hear a lot of this information in the media. For example, you might hear them talking about the average of this and the median of that. And so you want to understand what this is all about. But also, this is very, very helpful information when it comes time to planning your own finances. Okay. So, in other words, imagine yourself trying to put together a portfolio of stocks for your investments, your retirement rather. And so you've got to understand what these measures are all about in order to make the right decisions. So these prove to be very important topics. They're also very interesting. I think you'll agree with me when we're done that these last two chapters may be the most interesting two in the whole course. And in some cases, they can even be kind of fun because they can be used for a lot of very different types of situations. So now, what we're going to actually do here is look at a couple of videos that'll introduce these topics, and then we'll get started with the actual chapter. All right, so let's see hold on. I have to look at my list here. Oh, here we go. So this first one I think you'll find to be quite interesting. It's meant to be an introduction to what we're doing, and it's also just fun for its own sake. So let me send this to you. All right, let's check this out.
Everyone manages money differently.
Okay, are we done? All right, so the next one is a little different because this one involves actual probability. So we'll look at that one as well. These are both meant to be introductions to where we're going in this chapter. I just want you to get a feel for what's coming up. So this next one is very interesting. It's very intuitively clear what he's talking about, and it's actually kind of fun. So let me show this to you. I think you'll like it. All right, let's check this out. All right, are we all done? All right. So now you have a feel for where we're going in this chapter. So we're going to actually start not with the probability theory, but with the counting, because this will provide us with several techniques that we can use to understand probability theory. So that's why we looked at the video with the deck of cards, because they were talking about something very important that we'll be seeing here, and that was how many ways are there to arrange the deck of cards. So we're going to start out by looking at several important ideas here that fall into a branch of mathematics called combinatorics, which is the science of counting. Now, you might say to yourself, well, I know how to count, so why do we need to do this? But we're counting in a very specific way certain types of situations that can show up in statistics and probability theory. So we're going to begin by noting that with probability theory, what we're trying to accomplish is to create a mathematical framework for measuring uncertainty. So if I wanted to know, for example, the likelihood of getting a 7 with a pair of dice 3 times in a row or something like that, I have to have some mathematical model that helps explain how dice work when we roll them and how likely it is that certain combinations will turn up. So we're going to start with a very important idea, which is known as the fundamental counting principle. Now, what this refers to is what we were looking at in the video, arrangements. And if you remember, with the deck of cards, we took all the cards and shuffled them. And so what happens is we now have all 52 cards arranged in a certain way that, like you said in the video, may have never actually happened before in the entire history of the universe, because there are so many different ways of arranging a deck of cards. So we're going to start out with a much simpler example, which will be a lot easier to visualize than 52 cards in a deck. Instead, we're going to start out with a case where, imagine yourself in the future making tons of money, and you live in a mansion where you actually have a 3-car garage, right? You've got so much money that you bought a house that has a 3-car garage. So let's imagine how that looks. You've got the 3 garages left to right, and you also happen to own 3 really snazzy cars, an Infiniti, a Lexus, and a Mercedes. So here's the big question. How many different ways can I park my cars in these 3 garages? Oh, that's an interesting question. How do I go about solving this problem? Well, one thing we can do, because this is such a small set of cars, we could follow what's called the brute force approach, where we just list all the possibilities. Okay, there aren't that many of them, so we can just sit down and make up a list and show how the cars can be parked in these garages. And so that comes up in the next slide, where I've replaced obviously the word Infiniti with an I, the word Lexus with an L, and the Mercedes with an M. All right, so let's take a look and see how many different ways this can happen. All right, so you notice what I've done. I've written them out from left to right, and in each case, I'm basically changing the order of the letters. Each time I have a new, what's called arrangement of the letters that we have not seen before. So if you look at all 6 of these cases, you'll see that in no case do we have the exact sequence of letters, the exact same sequence of letters. Okay, so we have ILM, IML, all the way down to MLI. Those are the only 6 ways I can park my car in this 3-car garage. And so once you've listed them all out, you can see that there are 6 of them. But as they discussed in the video, there's an easier way of doing this that does not require us to write out the entire list. What is that way? Well, here's how we have to think about it. Suppose I'm sitting there, all 3 of my cars are parked out on the lawn, and I'm deciding how to park them in my garages. Initially, all the garages are empty. So for the first garage, I actually have 3 different choices available to me. All 3 cars are still available, so therefore there are 3 different ways I can park my cars, one of the cars in the first garage. But once I've chosen that first car, when it comes time to selecting the cars for garage number 2, there's only 2 left. So while there's 3 ways of filling garage 1, there's only 2 ways of filling garage 2. And once I've made the decision as to which cars to park in garages 1 and 2, there's only one way I can park a car in the third garage because only one is left. All right, so remember, there's 3 ways of parking in the first garage, 2 in the second, and 1 in the third. So I've summarized this on the next set of slides. Before I go on further, there's another analogy that I wanted to show you here. Imagine you have room on your wall for 3 posters hanging from left to right, let's say. How many different ways can you hang your posters? Well, let's find out. But first, let's note that each of these choices is called an arrangement. Now, by the way, because it's 3, just like we had with the cars, you can see that whether these are cars or posters, there are 6 different ways of arranging them. And so the answer to this question would be 6. There are 6 different ways of hanging 3 posters, each of which is known as an arrangement. So anyway, back to the car example. In the first garage, we have 3 different cars to choose from. For the second garage, there are only 2 cars left. So therefore, we have 2 choices. And for the third garage, there's only 1 left. So we only have 1 choice. So therefore, the number of ways we can park the cars, here's a summary of that: 3 ways for the first car, 2 for the second, and 1 for the last one. If I multiply those out, that tells me that there are 6 different ways I can park those cars. Or in other words, 6 different arrangements can be created from the 3 cars. So I hope that makes logical sense. With 3 objects, there will therefore be 6 different ways of arranging them. So that raises an interesting question. Suppose now I become even wealthier and I move into a bigger house that now has a 4-car garage. And I've got 4 cars. Let's say that I move into that bigger house and I decide to add a Rolls Royce to my collection. How many different ways can I park the cars now? Well, we don't want to write them all out because there's too many of them, but we can use the same logic we had earlier, which is that there are 4 ways of parking the first car. There are 3 ways of parking the second car. There are 2 ways of parking the third car, and there's only 1 way of parking the fourth car. So therefore, the number of choices is 4 times 3 times 2 times 1, which is 24. So the number grows very, very quickly. So that's why when we had 52 cards in a deck, the number of possibilities was so enormous that, like you said in the video, the chances are that each time you shuffle up the deck, you've created a new arrangement that's never been seen before in the history of the universe, just because the number is so enormous. But with cars, 4 cars, this is not that huge. It's only 24. Now, suppose I had 5 cars. You can probably guess where this is going. If there are 5 garages and 5 cars, the number of ways of parking the 5 cars is, and then it's just 5 times 4 times 3 times 2 times 1, and that gives me 120. So we went from 6 to 24 to 120 when we went from 3 garages to 4 to 5. So you can see the number of arrangements is growing very, very rapidly. But it's always the same logic in each case. How many different ways can we do this? Here it's 5 times 4 times 3 times 2 times 1. Now, it turns out that there exists a mathematical operator which will help us with these types of problems. Unfortunately, it is not on your calculator, if you're using the iPhone, that is. But it's easy to do it yourself anyway. What do I mean by that? All right. Well, first of all, this amazing mathematical operator is called factorial. And it is written with an exclamation point. So what you're seeing here is pronounced n factorial. All right, n factorial. Now, if you have a different calculator or a more advanced one, especially, there's at least a possibility that you do have it on your calculator. You may want to for it. If not, that's not a problem because it's easy to do it ourselves. But of course, it would be nice if you have it. Apparently, the creators of this iPhone calculator did not think that we were going to need it. Well, oh, wait a minute. Oh my God. I think I was mistaken. I think I may have accidentally found it. Hold on a second. I didn't realize this was even here. Oh, well, that changes everything. I'll tell you what, go look at your calculator. And by the way, before we go any further, I just want to mention that the way factorial works is the same way as the examples we were just looking at. The only two that you might find surprising are that 0 factorial and 1 factorial both equal 1. But then after that, what happens is in each case, you're multiplying this number by the previous integers, basically. So that, for example, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is, of course, 6. And then the rest of them follow along in exactly the same pattern. So, for example, what about 4 factorial? What do you suppose that would look like? Well, we've already seen with the 4-car garage example that if I multiply 4 times 3 times 2 times 1, that will give me 24. All right, so let's see that written down here on the next slide. Okay, and then we've already seen that 5 factorial then must be 5 times 4 times 3 times 2 times 1 equals 120. 6 factorial would therefore be 6 times 5 times 4 times 3 times 2 times 1 equals 720. Okay, now, how about this calculator, which I just noticed it does have the factorial operator. I didn't even realize it. So how do you use it? So if you look in the bottom left-hand corner, you'll find that it's there. It's labeled X factorial. So let's try it out on 4. So in order to reproduce this, you would hit 4 and then X factorial, and it will automatically show you that the value is 24. So there it is. I didn't realize it was here. So that's going to save you some time at least. How about 5 factorial? Just hit 5 factorial and confirm that it gives you 120. And then number 6 factorial, let's try that again. And that, of course, gives us 6 factorial, which is 720. Now let's try a really big one. Let's go to the next page, the next slide, and let's try 10. 10 factorial. Let's see how huge that is. Okay, so 10 factorial on your calculator will be 10 followed by the factorial key. And look how huge it's getting. Over 3 million. Well, that was fast. 6 factorial was 720. 10 factorial is over 3.6 million. And if you think that's big, let's try 30 factorial. Oh my God, the calculator is freaking out. So when you try that, you'll notice that this is what pops up on your calculator. And as it turns out, this is simply scientific notation for 2.6525, et cetera, times 10 to the 32nd power. That is a big, big number. That's why they're requiring scientific notation, because it will not fit otherwise. Okay. So, I did chop off some of the decimals, but it's approximately 2.6525. E32 means 2.6525 times 10 to the 32nd power, which is enormous. And in fact, if you remember from the video where they mentioned 52 factorial, then the number of arrangements of a deck of cards would be through the roof. In fact, it may be the case that your calculator, it will actually not be able to calculate it. It's so large. Let's find out. Some calculators are limited in how large. Oh no, it's here. 8.0658 times 10 to the 67th power. I mean, those are the kinds of numbers that there might not even be that many atoms in the entire universe. That's how big this number is. Wow. So they can get big, but always remember, these can be interpreted as the number of ways of arranging that many objects. So this is the number of ways or number of arrangements that are possible of a deck of cards. This down here, like if you had a game with only 10 cards, then the number of possibilities or arrangements would be about 3.6 million. Or if you had just the biggest parking garage of all time with 10 slots, this is how many ways you could park 10 cars. All right, so let's do a quick, simple example, which I'm sure you'll have no trouble with whatsoever. A small museum has enough wall space to hang 4 new paintings by this famous new artist. Now, this artist specializes in making a canvas, which is white with a single colored dot somewhere on the canvas. So this artist is now all the rage, and his or her works are selling for millions of dollars. So you decide you're so rich now that you're going to buy a complete set by this fantastic new painter. And these fantastic new paintings have to be hung on your wall. How many ways can we arrange them? Okay, well, you already know the answer to that is 4 factorial. Right? 4 factorial. And therefore, the correct answer is 24. There are 24 different ways to arrange your fabulous new paintings. Of course, now in this case, it's possible that they were meant to go in like that order you're seeing here, in which case you want to hang them this way. But in principle, there are 24 ways to hang these paintings. All right, so does everyone understand this concept of arrangements and how the factorial operator works? Make sure you can do this on your calculator because we're going to need it. All right, well, if you're comfortable, now here's the thing. This is more or less where I left off with the other class. I don't want to get too far ahead of them. So even though it's a little early, I would like to stop right here. Now, don't forget, what I expect you to do for Monday is to finish up these chapter 8 problems so that we can go over them on Monday together and make sure you really understand what we did in chapter 8. All right, so that's your top priority. If we don't run out of time on Monday, then we'll get back to this material. All right, so in the meantime, though, why don't we stop right here? And on Monday, we'll go over this chapter 8 problem set and then possibly some more new material in chapter 11. And I also have a lot of interesting new videos to go with chapter 11 as well. There's something about this material that lends itself well to videos. So don't worry, we've got some fun ones coming along our way. All right, so if there's no last minute questions, I guess we'll stop right here and I'll see you all on Monday.
Bye. Thank you.
Okay, bye.
Thank you. Have a good weekend.
You too.
Thank you.
Okay, bye.